Hello, everyone, and welcome to the NC presentation, Accelerate and Optimize with Production and Prediction. My name is Christopher Parker. I'm an applications engineer and NC specialist here at Hexagon, and thank you for taking the time to join me today. What I'll be showing you is an overview of the NC software, where we're going to use the machine digital twin to verify the process before you would, in theory, send the job to the shop floor. And this saves time by using the software to catch any issues ahead of time inside the programming room rather than out on the shop floor, so you can keep the machine producing parts. And why is this any different than the CAM that's already included in your software? Well, it's different because NC engine is running and reacting to the true post-process G-code, just like your real machine. It's not running the API of the CAM before you hit the post-process button, which you know when you do, you can see some discrepancies in the behavior of the toolpaths. Also, NC incorporates all subroutines or macros from the memory of your real machine into the digital twin. That way, there isn't a single motion that NC or the environment inside there isn't accounting for. So, here's an overview of what we're about to see today. The first thing we're going to see today is G-code validation, so anything that would alarm out the real machine, including things like out-of-range motion or overtravels, program syntax errors like G or M codes that are undefined in the controller, inconsistencies in the programs, all those sorts of things. And you'll see a full toolpath preview when NC does this automatically at the beginning, so you can make sure that you're in the right spot in the machine to begin with. Then we're going to watch the high-end simulation, and this is everything to do with motion and where the cutting occurs in the digital twin environment. And you'll catch any errors that have to do with rapid motions, cutting in material, overcutting with flute length, and any channel synchronization, if you have a multi-channel machine, can also be lined up in this step as well. From there, we'll move to the visual part inspection, where we're going to compare the original part model that you programmed from to what we just cut with the post-process G-code out of the rough stock in the digital twin environment. And it's going to let us know if we're gouging the part, if we're leaving excess material in areas, or if we're hitting our tolerances. And we'll use some measurement tools to do so, as well as some more analytical tools such as gouged material and surplus material. After those three verification processes, we can actually take it a step further and optimize the toolpath and machine power. We have three different levels to do so. The first is reducing air cutting motion, which will ultimately reduce part cycle time. The second is to optimize the in-material conditions, which will increase cutting tool life and produce smoother cuts. And finally, we can utilize the power of the actual machine, which not only allows us to bring all toolpaths that are underperforming up to the maximum power, but also to eliminate spindle overload risks if you have something programmed that is going to overrun the machine or spindle. And finally, we'll see some automatic documentation and collaboration. So NC can automatically create setup sheets for the shop floor, and anytime something changes in the virtual environment where you're verifying it, the setup sheets will automatically be changed as well. So the recalculation is automatic, which creates greater workshop synergy between the operator and the programmer, and it can also help to reduce new setup time. Then we'll see some areas where you can control in-process dimensioning without taking the part off the actual machine using something we call auto control. And finally, we have something called the NC Player, which is a license-free version of the software that you can load onto any Windows tablet or computer at the real machine or right next to it. And you can play the entire simulation, which we're about to see. You can take measurements off the part. Basically an entire version of software, except it locks what the programmer has done, so you can't edit or create anything new on the shop floor. And that's exactly what I'll show you today. So I'll switch over to my NC home screen and we can get started. Okay, so this is the main home screen for NC. If you notice across the bar at the top, it says Haas UMC 750, and this is what we call a working environment. And inside that environment, you also have a list of jobs that are already created. So I have this one created on this machine ready to go. And if I single click on it, it gives me a preview of my last view that I saved inside the environment, as well as any resources or pieces of the fixturing part stock that are inside there. So it's a really easy way to kind of check what's inside the project without entering and exiting a bunch of times to find maybe you wanted a particular program name, which you can see down there. If I do double click it, it starts what we call the 3-step process. So step 1 was that syntax error check. Anything that would alarm out the real machine is getting defined up front, and you'll see all those errors coming into the information window at the bottom automatically. And then as I was saying, the toolpath wireframes get populated automatically. So there's the screenshot we saw at the very beginning, and you can verify that you're in the right location at the machine before we even get going. Then step 2 is the actual simulation. So that's where that's found, and that's where you can play the material removal. And when you're in the 5-axis view, see all the axes of the machine moving around so that you can verify everything is rotating as you would expect after you've post-processed the code. And at the end of that, you run this comparison tool. And again, that's comparing the original part model to what we just cut in the G code. Your red is your gouge, your blue is your excess, and your green is hitting your specified tolerance, which we can set job by job or for your overall environment if everything was kind of standardized. At the end of that, we'll move over here to do the optimization. And at the end of that, we'll go ahead and do some documentation. And that's the process that we outlined in the beginning and we'll get through today. But before we jump into all that, I'm going to walk you around the screen a little bit so that you know what you're looking at as we're going through everything and have a little bit better of idea where I'm kind of navigating as we go. So the left-hand side over here is what we call the job tree. And this is set up, you can kind of think of it as being set up in the same exact way that you would set up the job on the real shop floor. You have the ultimate piece that you're making. So this would be the final part number or something that you wanted to create through however many processes that you're running. You have the certain process that you're running. So this one's just a single operation. You could call this op1, op10, something like that. And then you have the machine it's running on. So we're going to do this operation on the Haas UMC 750. Now on that, you'll have the machine table, which you can mount setups to. And in this particular option, we have 2 setups that are part of this process. We have a first setup that's going to machine the top side of the part, and then we're going to use some commands to flip it to the other side and re-grab it with the vise, and then do the setup and the machining for the back side. And you have 2 sections here. The first down here is called the tool library. So you can think of this sort of like your tool crib. Then we also have the tool magazine, which actually looks inside the G code, and based on what tool calls are called from the G code, those are loaded for simulation and material removal. Next up down here, we have what's called the initialization, and this is what tells NCSimul where in space to start the program. You'll spend most of your time in the Origins tab, and this mimics your machine panel at the real machine. So based on whatever your machine panel would say, if you're using P0 or P1, something different than G54, 55, this machine panel would mimic it. But basically, you choose the reference that you want and where in space to start. And then finally, we have the post-process G code. This is the same exact one that's running at the real machine. Now from there, I'll move to the bottom section here, which is called the information window, as I mentioned before. The first one we already saw, so we saw our syntax error checks. When we do run the simulation, any collisions will also populate in that window there. So the next tab over is the status tab. And as a note, all 3 of these windows inside NCSimul are always synced or dynamically updating. So anytime I kind of move throughout the G code, click on a particular line, it's going to line up my machine to that location and update the status of what's happening on that line. So we can see that we're inside a tool change macro, if we're inside of that, whatever tool number that you're running, the spindle rotation and direction, your point in space based on the active reference or the machine position, if you're using cutter comp or if it's off, and so on and so on. Next one over, we have an info tab, and this gives you the overall for the programs and is also part of step 1 when it's done. So if you look at those tool sequences, you'll see the same ones in the table here. And for each sequence, you'll see how much time that tool was running, how much of that was actually cutting for versus in rapid, your feeds and speeds, mins and maxes, working distance. Still dynamic with the other windows as well. So any of these cells, if I wanted to see where that tool sequence 1 reached the F max of 100 inches per minute, I just click right inside that cell. It brings me to the line of G code where I hit that F100 and shows me where in my part I was machining when that occurred. The other nice thing about this window is without even running the actual simulation, just based on the feeds and speeds and the parameters of the digital twin, such as machine axis accelerations and decelerations and tool change, time for tool change, and the macros involved in that, you can get a cycle time accuracy displayed here within 3%. Next tab over is a variables tab. So if you have any looping or conditional formatting that you've programmed inside your G code, all you have to do is come over here and choose the variable that you need to track, say add it to the right, and then make sure as you move throughout the program, if that value is getting taken and stored and it gets updated, you can make sure it's storing or taking the good value. And then finally down at the bottom here, and we'll see it a little bit more when we get into the optimization, it'll be a little bit more interesting, so I'll gloss over it for now. But we have a graphing tab, which you can click and move bidirectionally in the window, again, moving the machine and moving the G code. You can jump tool to tool, you can jump stop to stop, and you'll see all the colors will line up to the surfaces inside the machine part per tool change. And right now we're just in feed rate by minute, but again, once we get into the optimization, you'll see more parameters, but certainly we could add like something like spindle speed now and flip between them to view those on the axes or view them on the same axes as well if it made any sense to do so. On the right-hand side over here, we have what's called the program window. And again, it's that same post-process G code plus any of those subroutines or macros that we incorporated into the digital twin. So as I was saying, for example, we have a tool change macro for T1M6 that's pulled off your real-life machine, and I can just hit the plus sign to see the decompose motion occurring in the background whenever the G code calls that. So again, it's really good for both cycle time and to make sure that we don't have any unforeseen collisions when we're approaching or leaving the part to do a tool change, and you know that this is exactly what's happening in the real-life machine too. And then finally, before we get started, we just have the main 3D window with all the graphics. And you have two ways of viewing the simulation environment. You have this full machine view, where you'll see all the axes in 5-axis motion, I should say. And then you also have the table view, which I can switch to here. And it aligns you in the Z-axis direction and just shows the tool coming around, removing material, which makes it a little bit easier to see and a little bit more similar to how the cam presents itself in the simulation. But what you're looking at here is your red lines are your rapid motions, your blue is your feeding, and if you had cutter comp active at any point, you would see those highlighted with a green toolpath wireframe outline. And as you're viewing these during the simulation, you're certainly welcome to do two at the same time. So if I go up to the display tab and just say machine part, I can split the screen and I can have the full 5-axis motion happening on one side and just kind of hide the toolpath wireframes here and just see the material removal coming on the other side. So you can get a good visual representation of both sides of that. So that's the quick rundown of exactly what we're going to use to step through all this process. And I'm going to jump back to our simulation process errors and go ahead and say we're going to start now at process 1. So syntax error check, anything that's going to alarm out the real machine. And to let you know, this happens after you created your job tree, which can be entirely created in NC-Simul. So you're certainly welcome to import setups, import CAD models to create the fixturing and rough stocks, create tools in the library like we saw. But if you have one of the major CAM systems, you can import all of this data automatically. So if you already have those things in your environment that you've kind of been programming from, we have connectors that can send all that data over so you don't have to build any of that twice. But to start off, we're going to move top to bottom throughout this information window to take care of all the errors. And what you do is just click right on the error message, and it's going to, again, align my machine and show me what the problem area or the problem block was inside the code. And what the language is telling me is that my z-axis is out of range by 1 inch, and inside the parentheses, it'll give you the limits of the machine. So basically, I'm allowed to go from negative 23.6 inches to 0, but currently, based on our assembly location, the retract is making us go to Z1. So all I have to do inside NC is come over here to this quick edited mode. I click on the pencil with the star icon, and then I can go right in there and modify the code directly. And then I just hit that same icon again. It asks me, do I want to take into account changes? I say yes. NC will automatically reruns that first step for the syntax error check and make sure that that new value is good. And that's all you have to do for step 1, kind of move top to bottom, get rid of any of those error messages until this window is blank and this button down here is green, which means you're good for step 1, and we can do step 2 or move to step 2 for the actual simulation. Now, when I open the simulation ribbon, really you're using 3 main buttons inside here. You have a reset button, you have a play button, and then you have a speed of simulation slider, so how fast you want to see the material removal come off the part. So I'll start the simulation process in real time for us. And again, I'm in this full 5-axis motion. So as the tool change occurs, it goes and gets the tool and then approaches the machine to start the simulation. And I'm going to just shut off the toolpath wireframes so we can see something happening. And again, as this is occurring, I can be changing the simulation speed that I want to see. So maybe I'll move it up to block. So now we're doing 2 blocks per second. I can be zooming in and out. I can pan left and right. I can be rotating around the environment if I needed to get closer in. Again, I'm just going to speed it up a little bit more so we get somewhere. And then as you saw there, we reached the end of the first operation. So the part flipped automatically for us. And I'll show you exactly how to do that. And we started machining the backside and continuing on from there. And if you notice each tool that's coming in, and granted this one was doing a lot of the material at once, but it'll cut in a different color so you can kind of verify that each tool is getting to do work. And as you start to hit collision objects, they'll be populated at the bottom down here. So we're having some collisions between the active tool and the fixture, the Raptor B vise, and the same thing with tool number 6. So during this, I can pause it at any given time too. And if you want to see exactly what was machining a particular surface, I can just come in here, click on that surface. It's going to automatically line up my tool and my program to that location. So you can always kind of jump back and forth between what you're seeing, what angle you're at in the 5 axes, and where you're at in the code. So one thing we saw right away with these collision objects is that the tool and the fixturing are colliding. So either we're going too deep inside the pocket in here, or if we're moving around the edge, maybe we needed to define the fixturing as machinable so we could go ahead and chamfer that edge, or maybe we need to pick up our chamfer a little bit so that we're not colliding with the fixture if we're not supposed to. So it's kind of up to you how you want to do that. We could actually change the depth of cut on this, or in this case, I'm just going to define the fixturing as machinable so that we can see how that works as well. And to do that, all you have to do is enter the setup. So we're on the second operation. So I'm going to enter the setup for the op20. And then I'm going to go into the particular fixture files that I want to set as machinable and do so. So we have 3 different fixtures, one for each of the jaws and then one for the base. So we're going to leave the base as collision object, and then we're going to define the jaws as machinable. And to do that, I just go in and right click and say clamp property. And I come up to the clamp type, and it is mobile because we were moving them back and forth to kind of clamp on them, but I can also define them as machinable at the same time. So I'm going to apply that to both of the properties of the clamps, and then just apply from my setup back to my main machining environment. And the other thing that you'll notice right here is we have these pieces that would fall off in the real machine that could be considered potentially as collision objects that we don't want to identify in NC Simul. If you have a lot of these little pieces, I can just click on the main machine part and say keep as machine part. That way it's going to delete any of the little scraps around it. Or if you have just a couple like this, I can actually click directly on them and just say delete as scraps. And do you want to remove? Yes. And I can do that to both the little ones, and they're outside of the environment or dropped off into the machine at this point. So that way they're not in the way for any potential collisions. And also, if you wanted to save the result of this final piece, you can actually export the stock. And of course, you don't want those floating pieces if you're exporting the stock. But you can just right click and say export. And it's going to give you the option for certain formats. So you can export in STL, you can export in STEP or Parasolid, and NCMac is NCSimul's internal format. If you wanted to go ahead and use it for a different operation in here, it works really, really quickly inside NCSimul. So far, those are the manual ways to do it, but we also have particular functions that we can just add into the process to do all of that automatically for us. And all of those are located in the Program tab and under our functions. And since the setup tree kind of reads top to bottom, you want to insert them where they're going to occur throughout your process. So the first one that I'm going to add in is the scraps management. And this just has to be added before the first instance of material removal occurs. So what I'm going to do is just click right on the initialization. So I'm going to put it in right after that and go up to my function and say scraps management. That's the function that manages that. And you just tell it which type of machining you're doing, so milling or turning. In this case, we're doing the milling, and the criteria to keep. So in this case, we're going to want to keep the largest volume anytime two different volumes are separated, and just say OK. And then you can see it adds the function scrap management just before we have our G-code. And then you notice that we have a modified G-code just letting us know that we changed earlier that Z0 to Z1. And that's something different than we imported with the original post-process code. The other automatic function that we can add at the very end is the export stock. So anytime the simulation finishes, it's automatically going to export the result to our simulations folder inside NCSimul. So I'm going to put that at the very end. I'll just click on my program then. That way it'll go after that. And I go back up to the same program tab and the functions. And this time I choose the export stock function. Again, you can choose the file format. So I'm just going to export in STEP in this case. And here's that simulations folder that it exports to. And I'm just going to give it a name, the unit that you want to export in, so inch is fine, and the reference that you want to do. So we're just going to reference it from our 0 setup and say OK. And now every time the simulation is run all the way through, it's going to create that model automatically for us in that location. And the last things I can show you that we could add automatically were the setup change functions. So as we saw during the simulation very briefly, NCSimul automatically flipped the part and continued to machine on the other side. So basically it changed from setup up 10 to setup up 20. And you can see inside the G-code, it's warning the operator that it needs to flip the part for up 2. So what you can do, again, same functions tab, we can go down here to setup change. And you choose the table that you want to change the setup on. We just have one table on this machine. And then you want to choose the setup that you're going to load. So we're going to load setup up 20 in this case, and that will switch it from our original up 10 that's loaded originally to what we want. And we'll just say OK. So it's added to our process. And also, if you look inside the G-code, there'll be an interactive comment where NCSimul will do it automatically. The other thing I'm going to turn on this time when we run it all the way through is intermediate stocks. And I'm also going to put it on end result, so we're not going to see anything happen until we get to the final thing, and the final piece will pop up so long as we have no collisions. So that's what we want to verify one last time. I'm just going to hit continuous. But as I was saying, with the intermediate stocks active, you can look at all the tool sequences that'll preload, and then as each one gets finished, you see this green icon here, meaning it's holding all the material removal in memory. And now when you click throughout the G-code at the end of the simulation, you'll be able to automatically update to exactly where that sequence finished machining at any given point. And the other nice thing about doing it this way is if you make any modifications inside the G-code as you're doing this, say you made a modification in tool sequence 7, tool sequences 1 through 6 were the same, NCSim will just jump directly to tool sequence 7, knowing that the G code is exactly the same as what it ran the first time around, and then begin the simulation and material removal at 7, just in case your code did anything different. Okay, so there's our final piece. Again, if I expand this, we don't have any more process errors, meaning we alleviated everything that was colliding inside the environment. And this button is green again, meaning we're now good for step 1 and step 2. And all that's left is to make sure that we cut a good piece. So to do that, first off, we have some measurement tools. And from here, you can do things like take radius measurements, you can take hole-to-hole measurements or depth of drilling, angles of areas, but ones that you use most often, I use point-to-plane a lot. That's basically a distance measurement. So if I wanted to see maybe exactly how much leeway I had on that chamfer tool or how much I had to bring it up, I just click once on the surface to create a plane, and then I can click anywhere else to take a measurement from there and get the distance of that stick out in that environment. And anything will work. So you can do off the part model, off the fixture, off the rough stock, pre-machined or post-machined, any of the machine environment as well, so like the tabling, all of that sort of thing works. Then we can jump back to the simulation tab and do the comparison, which I was mentioning at the very, very beginning. So here's kind of the intermediate step after we did the first operation, but I can go down to the bottom here and flip it to the result of operation 2 as well. So again, green is within your tolerance. Red are your gouged areas, so maybe the chamfering wasn't present on the tool part model. And then blue would be excess material for the next operation, like we sort of saw in the first one there. And all of these are customizable, so if I wanted to set my step maybe plus or minus 4 thou in my green area, I just add that to that, and it creates the scale based on there. But if you didn't want your scale to be completely uniform, I can also drag any of these fields directly in here to make them larger or smaller for each area. And the last tool that we can use is called cutting planes or cut plane. I can just come in here and create a section wherever I want. I can pick my angle or axes that I want to do it on, and I'm just going to turn to our table view. It's a little bit easier to see. But basically, if you wanted to see any internal features before cutting apart a first piece on the shop floor, I just go ahead and add a cutting plane, and then I can drag it to wherever I want inside the part. The other features I mentioned in the original slides were the gouge material and surplus material. So if I start that, it's going to create a table for me at the bottom with a little bit more information than just the colors. It'll give me a volumetric output about any place that the tool touched the original part model, which I can then sort by volume, so I can see my biggest problem areas and what tool was running, exactly where that was coming in and occurring in the environment, and all the way down for each instance. And you can export this data to Excel, or you can just kind of come in and fix it inside NCSim. And the surplus material works exactly the same way, just it'll show you only the blue areas instead of the red areas. So I'm just going to scroll down and click to the end of the sequence, because since we have the intermediate stocks on, it's automatically updating to where I'm clicked inside the G code. But basically at this point, you know you're good for the entire 3-step process. We have a code that's not going to alarm out the machine when it gets loaded. We have a simulation process that doesn't have any more collision errors. And we've verified that the piece we just cut looks like what we want to actually cut and be able to inspect first time in the shop floor. So at that point, what you could do is come back down here to Save Program. And since it's again modified, I can just export this or output this as a save as basically. And you could decide whether to send that text file directly to the machinist on the shop floor through the network, or if you store them in some location where they're ready to go when the machine or when the part's ready to be machined. So that's your basic functionality of NCSim, and now it's time to add some fancy things like optimization and documentation. So we'll do the optimization first. And again, this is contingent on the fact that we verified we have a good process that we can now take a step further. Okay, so when I open it, we'll have some settings to do up front. So basically, the first one that you want to view is the segmentation value, and it's a percentage of the tool diameter that the simulation will move before cutting conditions are recalculated. Then we have a tapes tab. You can decide which programs, if you have multiple inside your operation, that you want to optimize. So obviously we're not going to optimize anything inside the memory. We just want to make sure that we're optimizing the 1203 Haas demo main program. Then inside that program, you're going to have the opportunity to check or uncheck any tool sequences that you want to optimize as well. So say you use the same tool in two different sequences, one for roughing and one for finishing. You could say, hey, maybe I only want to optimize the roughing pass. I like the way my finishing is cutting. We'll just leave that one alone. So even though it's the same tool number, you're going to have an extra opportunity to be able to clarify if you want to use it or not. And all I have to do from here is just say compute. So NC at this point is going to run a baseline simulation for all the conditions inside material. It's going to gather the maximum chip thickness, maximum chip flow, maximum feed per tooth, radial engagement, depth engagement, and considering or assuming that you don't break any tools when you ran this the first time at the machine, we're going to use those maximums and bring anything up that's lacking to those capacities up to that level so that we can kind of optimize every single thing to its maximum. Additionally, we can use the power of the machine to kind of cap how much engagement we have. That way we're not overrunning the spindle and risking breaking a tool or anything of the sort. So now that it's done the baseline simulation, you can go down into the cut analysis, which is pre-optimization. And like I was saying, all of those conditions like engagements and feed per tooth and max flow and max power of the machine are all here. So you could kind of quickly scan through here and see if anything is out of the ordinary. So now what I can do is go back to the top and actually set the settings for the optimization. And as we were saying, there's a few different levels. One is the air cutting, where just any time that NC senses that the tool is not engaged in the material, we can tell it to upgrade that to an Fmax based on the machine or just a G0 and throw it into rapid. We can also do the adaptive, so in material, and this calculates exactly how much material that the tool is moving at any given point in time per the 25% tool diameter that we set originally. And then if it's not moving through enough material, we can increase the feed rate. And if it's moving through a large amount of material or just the right amount, we can kind of slow it down. So that's the one we're going to do today because we can also include the air cutting inside that. And we can also include the power of the machine to use the cap for that when we're inside that as well. Then we're going to set our strategy. So you can say, go ahead and optimize for every single movement, or in this case, I'm just going to do movements that aren't plunging or ramping. And then based on the type of material, you can choose if you want to do a standard chip thickness or chip flow, which is volumetric. So we recommend chip flow for soft materials and chip thickness for hard materials. So since we're doing the aluminum, I just go ahead and click the equation for the soft material and hit apply. And based on that original cut analysis, it fills in all of these fields. And here's the option if you wanted to limit the power of the machine and say maybe we only wanted that maximum tool to go to 5 kilowatts instead of the 7 we saw. You can max it out or limit the max with that PC there. Next one over is securities. So you can set the values where you revert to your original feed rates regardless of the optimization based on engagement and retracts of pre-machined and untouched materials. So this would be the untouched, and once it's touched once, you know exactly where it is in the environment just as you would at the real machine. That way you can kind of tighten it down before you slow it back up with the optimization. And then as I was mentioning, for the feed rates, you can either put your Fmax for the UMC 750 in here, or you can just say throw it into rapid every time. Usually I do Fmax, but we'll just do rapid for today. And then all you have to do, if you want to save the process, you can hit save there and come up here and let's optimize based on those conditions. So since the bulk of the calculation is all done in the initial cut analysis, the optimization is actually really quick, which is nice because if you want to go in and change some settings and re-optimize, you're only doing that little last step that we just saw, not the full-on computation that we did at the beginning. So there's our final result. And you can look down here into our cut info, and per operation, you can see exactly what the original values or original time was and what our optimized time was and the difference between that. So again, operation by operation, but you can also go right to the top and look at the overall. So originally, we had a program that was about 12 and a half minutes, and after we optimized it, we're down just under 8 minutes, so we saved actually a lot, almost 5 minutes or 38% of the cycle time. And you can see exactly where that's coming from. A lot of it we put into Rapid here. We saved a lot of time outside of material, and additionally, a lot of time, well, also as well inside material. You can also hit compare, and now if you kind of zoom in, you can see that any feed rate that has been modified will show up in yellow in the 3D window. You know it's different than the original here. And also any feed rate that's been modified in the G code will be highlighted in purple. And NC Sim will automatically rewrite all these feed rates for you. It's just kind of warning you and showing you exactly where we've made any of our changes or something's running quicker. And then all you have to do at this point is come up to your settings and say where you want to output the process to and give it a name. And the other nice thing that NC Sim can automatically do is it can create a new blue folder like we saw at the very beginning with the same simulation process but called Optimize, and that way you can run the entire simulation again if you feel more comfortable doing it after NC Sim also quote-unquote post-processes it with the new feed rates, and then you can make sure that everything's good before you set it to the shop floor. And the last thing I want to show you is the documentation module. And to get the most out of this, you definitely want to make sure that the simulation has been run once all the way through. So since I kind of reset it with the optimization there, I'm just going to run it all the way through on end result one time more. But as you can see, since I'm not viewing anything, NC Sim can decode this really quickly. So I'm doing that 13-minute, 14-minute program that we saw before in about 5, 6, 7 seconds. And the reason I'm doing that is because I want the material removal at different sequences shown in the output of the documentation. Now the output or the final output is completely customizable, so whatever you want on your shop floor we can make happen. It's built on Fast Report, so every feature inside NC Sim gets exported automatically into the setup sheets. So if you change a tool stick out length or you change a holder that particular tool is using, all of this gets sent through automatically and updated automatically, so the machinist and the programmer are always on the same page if anything's changed. For instance, if I wanted to highlight where the pickup point for G54 was on the documentation, I just come over here to my G54 origin, which it shows me in the environment here, and I can hit this icon and say origin view to capture that view. I'll deactivate the original one and just set the new one as preferred. And now this is the picture that we're going to see when we process the documentation. Another example would be for a tool sequence. So say I wanted to show the result at the beginning and end of tool sequence 1 and what machining's been done. Might again be a little bit easier to see in table view. And I just come in with a piece of paper and say start of tool sequence view, which is that one, and end of tool sequence view, which is the one we saw there. And again, I'll just deactivate my first ones and set my other ones as preferred. So like I said, you could do this for every single sequence. Just do it for a couple so we can see the difference in the setup sheets. And then all you have to do, once you're happy with how everything looks, just come up here and say preview, and it's going to automatically create the documentation. Here's an example of one of the templates that we created, and obviously it's very extensive. There's a lot of sheets, so you wouldn't necessarily have to have all of these, but you can have like pictures of the part and the setup, the sequences and how long each one's running for, just a picture of the machine. And here's the G54 picture that we took, so the machinist knows exactly where in space that is based on machine home and what it should really look like inside the environment. And if we scroll down to that first sequence, those are the other two pictures we took. So the original start of the sequence and what it should be looking like in the machine once that first tool is done and we move to the second tool. And if we scroll way to the bottom, we'll get a tool list output. So again, this is one tool per page with every single bit of information that you can possibly have, but you could streamline this to have just a single page for all the tools and just the relevant information that you want on the shop floor. And if I back up a little bit, there's another thing you can do to kind of control your in-process dimensioning. Again, I just choose what sequence I kind of want to do the in-process at. So I'll just choose sequence 6 here. And I come up here to create. And I can create a new dimensioning page based on this. So maybe I want to control the thickness of one of these machined walls before I unload it just to make sure. You can just come over here and, for instance, I'm just going to say this one's the thickness and choose that surface. It'll create my first dimension called A. And then I can come in here and tell the inspection room how I want that measured. So it's a thickness. What tool do I want to use? I want to use calipers to make sure that that's okay. And then sort of just kind of build up anything in the environment that you want measured ahead of time. And of course, the same way as before, we could have a sheet that this outputs to inside our documentation, or just have its own documentation sheet. So this can all be exported in the same way as we saw just before. So that's kind of the end of everything I have to show you. I know it was a lot of information thrown at you all at once, but just to kind of summarize, I'm going to pull up a couple last slides so you can really kind of hone in on what we've covered today. The first thing was the G-code validation. So upon loading, NC-Sim will parse the G-code, and anything that would alarm out the real machine was caught up front. Then we ran the simulation, which was everything to do with motion, where the material removal actually came off the part, and we caught any collisions that we were going to run into there as well. After that, we did the visual part inspection, which compared the original part model to what we just cut out of the post-process G-code, and we saw any discrepancies at that level. After that, we did an optimization with air cutting, in material, and the power of the machine, ultimately reducing our cycle time and creating more consistent cuts. And then finally, we output some documentation from our process, which is completely customizable to whatever you want to see on your shop floor. We controlled some in-process dimensions to make sure that what we were cutting was okay at the given time before unloading at the machine. And we created an NC player file that was sent out to the shop floor so they can be seeing exactly what the programmer was envisioning inside the programming room. If there's anything you should remember to take away from today, it's these last 6 points. The first is NC-Simul's ease of use. Since it's based on Windows, everything is tab and icon based. When you right click, it does what you expect. It's really intuitive and easy to learn. Second is the strong 3-step process that guides you from one action to the next. And again, that was G-code verification, simulation and material removal, and part verification. Third is that we verify all macros and subroutines in their entirety. We gather all that information from your real-life machine. It's unique to every single machine on anybody's shop floor. And we create a digital twin based on that so you have a true representation of what's about to happen at your machine. Then we have the speed of simulation. So you saw that we had about a 13-minute program that we ran today that we ran in about 13 seconds, so almost a minute per second. The clarity of the 3D, we were zooming, panning, rotating as the simulation was happening. We were shutting on and off toolpath wireframes, switching between machine and table view, and we never had to stop for any instances. And lastly is the short learning curve. So today we have online training that's broken up into 2-hour sessions. The first 4 will focus entirely inside the NC-Simul software, and then the last 2 sessions will focus on your real-life projects coming from whatever CAM system you're using so that we can implement a process unique to your day-to-day that's going to be best for you. Okay, so with that, I'll open up the question and answer session. I'll try to get through as many questions as I can that were typed in the chat box, but if I don't get to yours or you want to take something particular or in more detail offline, you're certainly welcome to do that too. So again, my name is Christopher Parker, and you can reach me at christopher.parker@hexagon.com if you want to email me directly. You can also head to our website at www.ncsimul.com, which is the direct product page from the Hexagon website. And you can also view some more content on YouTube. If you just put in NC-Simul YouTube, you'll find it come up in the Google search, or you can follow that direct link to our particular page. So are there any questions that rolled in for me?